So thank the organizers for the wonderful week, and actually thank you for giving me extra 15 minutes to sleep this morning. Yeah. So yeah, I want to talk about some vanishing results for completed cohomology of Shimura varieties. So this is all joint work with Kaiwan and Lan, and some parts still in progress. So you the later in the talk. Yeah, so let me first introduce completed cohomology. It already appeared I guess several times in the past week, but I don't think anyone really wrote down the definition. So the completed cohomology. This was introduced by Emerton as some kind of space of p-adic automorphic forms. It doesn't. Emerton defined this for general locally symmetric spaces, but for the purpose of this talk, I will just restrict myself to the case of Shimura variety. But it doesn't have to be. You don't have to restrict it to the case of Shimura. So let me start with the Shimura datum, so G and X. So here, G is some reductive group over Q, and X is some Hermitian space with an action of GR, satisfying some axioms that I'm not going to repeat here. For example, you just take the G to be GL2, take X to be the union of the upper and the lower half plane. And to define Shimura variety, I also need to choose a level. So I can write here, right? Okay. So for an open compact subgroup, subgroup of the G of finite ideals, I can let me also put this neat condition, just some sufficiently small condition. I can look at the double posed go back. Okay. Which is just X times right quotient that. Okay, quotient by the Q points of G. So this is in general, so this complex manifold, but it turns out that actually I don't. It's an algebraic variety. So this is a Shimura variety of level K. With this neat condition, so that actually is a smooth complex manifold. So the idea of Emerton is that you can define some kind of a, well, I guess didn't write here, but throughout this talk we will fix a prime number P. So you can define some kind of p-adically completed cohomology as follows. So the idea is that you fix the level away from P. Throughout this talk, we will fix the level away from P. Some open compact subgroup, P finite. That also away from P, and then you vary the level at P. So this is usually called tame level. Here. Fine. So if you have a choose an open compact subgroup of GQP, you get the cohomology of level K upper P and K lower P. You can take its cohomology, it's the usual Betti cohomology, the mod P to the N coefficient. The idea is you first take the direct limit over no such level at P, then you take the inverse limit over N. And then this is this will be denoted by H2 tau I, and it's got the completed cohomology of tame level K upper P. Okay. So what kind of symmetry does this space have? So first, since I take the direct limit over all the levels at P, so it carries a continuous action of GQP. So I forgot to say, so you can equip this with the p-adic topology. I mean, p-adic topology from the inverse limit, and it carries an continuous. So it carries an continuous action of GQP. And also, actually, you have something more. So the Shimura varieties, as I say, so algebraic varieties, so over C, but actually they're defined over a number field. Let's say they're defined over some number field. Pick some number field. Well, you can take the smallest one, but some reflex field L. And then since the tau, I mean, all the varieties are defined over L. If you you identify this with a tau cohomology, then actually all these cohomology groups as an action of the Galois group, absolute Galois group of L. Bar over L. And also, as usual, so you have the Hecke operators away from P, acting on this the cohomology of these symmetric spaces. I want to be very precise here, but this is just Hecke algebra away from P. So okay, and so everything expected that so I mean, well, I didn't write down, but I mentioned that we expected this is some kind of space of the automorphic forms. But as you see, so here, really for h degree I get such a space. But what we expect is that's actually only in the middle degree completed cohomology. I mean, it's the most interesting one. So expectation actually some are theorems. So let D with the dimension of X, or also just the same as the dimension of the Shimura variety. Complex dimension. Now that's a real manifold, complex manifold. So we expect that it vanishes above middle degree. So they're actually in the Hodge type, I mean, this was first was proved by Schulze, basically showing that if you take the inverse limits of tower, you get some perfectory space, and then so this vanishing, and then there's some later generalization to abelian type, a pre-abelian type Shimura varieties. But so for the purpose of this talk, so I think we will invert P at the end. So I would just simplicity just invert P here. So actually, what is the theorem? So it's a result proved by Juan Esteban Rodriguez Camargo. is that actually for general Shimura variety, this is so torsion. So if you just invert P, so maybe we ignore the degree above D from now on. And as I mentioned, so expect that the middle degree is the most interesting degree. What do I mean by interesting? So I would just refer to Emerton's work on local global compatibility. I mean, just in the case of modular curve, he really has some description of the completed cohomology. I mean, relation with the local longhans or GL to QP. So modular curve. You can find the description in Emerton's paper. And so for this socket, we will just focus on this range. I mean, it's also interesting, but what we expect is that somehow the cohomology class are more non-generic compared with the cohomology classes appearing in the middle degree. So since I mentioned that there are three kind of symmetries here, so Heck symmetry, the symmetry of this group at P, the representation of Piatti-Lee group, and also the Galois group. So actually, you can talk about this kind of generic condition with respect to different this kind of symmetry. So, for example, the Heck action. So if you just restrict yourself to that Heck operators away from P, you know that actually the Heck action is non-generic in a certain sense. At least in the case of outside, but this was first by Riani Schulze. Later on generalized by many people, I guess, Koshiwara, and Lee. Sorry, I'm not too familiar with the current status of this part. But the idea is that if you look at the system of high eigenvalues appearing below middle degree, I mean, they can't be arbitrary. They had to be satisfy some condition. And the goal of this talk is to really focus on these two actions. So I will mainly focus on this and say something about what can we say about this action. It's really these two actions. So it's just the representation at P. And also this Galois action, I mean, that's just the absolute Galois group of Q, of a number field, but actually we will just restrict ourselves to a decomposition group at some place above P. Let me try to make this more precise now. Any questions so far?
Yeah, so there's no kind of Poincaré duality for the degrees here.
There is, but it's not a. But it's a more complicated. It's not like the naive Poincaré duality. You have to use the Iwasawa algebra to formulate the Poincaré duality. And yeah. Any other questions?
So there'll be non-torsion classes below the middle degree.
Yeah. Yeah. For example, H0 is just connected component. It's not zero. But... Okay. So what do I mean by I want to say these two actions? Well, let me first ignore. Just focus on this action to be generic. So this is a highly well, in general, it will be non-commutative. So I sort of want to say some the weight appearing below the middle degree non-generic. So we all know that if you want to talk about weight, you want to talk about the action of Lie algebra. But unfortunately, Lie algebra doesn't quite act on all the vectors here. So first thing you need to do is really to pass the subspace where you can't really talk about the action of Lie algebra. But Lie algebra is really action of some kind of derivation. So you want the action to satisfy some analytic conditions so that you can take derivative. So you want to put some analytic condition for the vectors here. So that leads to the following notion. So let me first, as I say, so I will just invert P. Okay, so then this is just a Piedi-Banach space. Representation of GQP actually the open uniboy is just given by h tilde I or the image of h tilde I. And actually this action is even unitary. Admissible representation. We will not need this. So definition, it already appears in Juan's talk. Explain a little bit more detail. So let me denote by h tilde ILA. The subspace of GQP locally analytic vectors. Okay, so what does it mean? So I look at all the vectors in this Banach space on which the action of GQP locally around the identity or locally around the identity can identify with some kind of p-adic unit disk. And then after doing this identification, I want this action locally is given by some convergent power series. Okay, so locally really means it's locally around some open neighborhood of the identity, and the analytic really just means that the action is given by power series, convergent power series. Sure. Well, this is a subspace, and it turns out it's a GQP invariant stable subspace. You might think, well, in general, I mean, why does there even exist such a vector? But in this case, because we know it's admissible, so actually, it's a general result of Schneider. That's actually, this is a dense subspace. And actually what they prove is much stronger in the sense that actually if you take any, for example, GQP, stable closed subspace, and if you take the locally analytic vectors inside, it's always a dense subspace. So it's basically, I want to say you don't lose too much information when passing to this subspace. For example, if you just fix this, you look at some high eigenspace and you take its locally analytic vectors. I mean, if you start with something non-zero, then this is still non-zero, so you don't lose too much. The second thing I want to mention is that, well, as I say, so we want to talk about weights, and on this subspace, so you have the action of Lie algebra. So the Lie algebra, I found that's this is the Lie algebra QP. And now to talk about weights, we can just consider the infinitesimal character. So let me denote by z g or simply z in we denote by z to be the center of the universal enveloping algebra of G. Then it will also act on H delta I. Now I'm going to state the main result. Other questions before I. So we'll first state the result, then explain what appears here. So let lambda be a character of Z. So here I'm just it takes value in QP. That's simply because my completed cohomology I just just invert P. But in general, if I really want to work with some field of coefficient, I can extend the field of coefficient to any extension of QP, completed extension of QP, and then allow more general field of coefficient here. So that's for simplicity. Let me just state the result with QP here. So this is really just for simplicity. So I would use this notation H delta I LA lambda to be the lambda isotypic part. H delta I LA. So the main theorem is that this is 0 below the middle degree if lambda is sufficiently regular. This will be our sort of a generic condition here. So let me define what sufficient regular here means. So here's lambda is sufficiently regular. If the following is true, so just some notation. So by Harshchandra, we can identify lambda the Val group orbits. Let me denote it by this bracket L lambda. So Val group orbits in the weight space. Space. And let me emphasize here. So usually you will see some shift by rows, so that you just consider the dot action. So here it's just the usual Val group action on the weight space. So there's no shift by row here. The usual action, not dot action. And then we say lambda is sufficiently regular if the pairing between lambda prime and all the co-roots, so for any lambda prime in the orbits, co-roots alpha check is not equal to 1 in the case of type ADE, and 1, 2 So type BC. And actually we can say we have a more refined result in type BC, but okay, for simplicity, let me just state in this way. Yeah, so that's the sufficient regular condition. So what's the relation with just being regular? So in the type ADE case, actually this is the same as being regular. For example, if you start with the dominant weight, regular dominant weight, if you look at the infinitesimal character, then it's a sufficient regular. So there's no distinction between sufficient regular and regular in type ADE case. They only differ in type BC case. Yeah, and the one reason I really don't think it should be that essential, but in type BC you have long roots and short roots, and somehow then you have this extra possibility of being. Yeah, that's just the limit of our method at the moment. That's the statement of our results.
Is this for arbitrary Shimura varieties?
Yeah, arbitrary Shimura varieties. Yeah. Yeah, maybe. I mean, the precise statement here is that I mean, if you let's say product of each type, I mean, for each factor, if you satisfy these, yeah. So I have one more remarks.
Can I ask a stupid question?
Yeah.
A really stupid question. So for like classical modular forms, weight 2 is irregular in your sense, and weight 1 is regular in your sense.
Exactly. Yes. Yeah, that's because this is after you shift by row.
Yeah, I understand.
Yeah, I like this. No, actually, it's important.
Yeah.
And I'm going to mention this example. Yeah, so I have a couple of remarks. Some are a bit technical, so that's why I don't want to give the precise statement here. So, so first thing is that there's a family version. Want to write it down. So, in the sense that well, here I just fix a infinitesimal character and look at the isotypic part. You might ask, well, what if I don't want to do this and just take the locally analytic vectors? And say something about that. Actually, it's also true. So I would just say this verbal is. So you can see that this kind of a sufficiently regular condition basically is just defined by some hypersurf hyperplane. Well, it's not hyperplane in the weight space. So actually in the spectrum of Z, so this non-sufficient regular locus is really some kind of codimension 1 locus. So what I really mean here is that if you just say this locus are defined by some function f, so if you invert f, then it will Q all the cohomology of below middle degree. That's what I mean by family version. You don't have to really fix this. First, well, and probably it's clear also from this formulation here that the weight doesn't have to be integral. You have can be p-adic, truly p-adic weights. But if you look at these conditions, so the more p-adic this weight is, actually the more sufficient regular. I mean, you have to be sort of integral to not to be sufficiently regular. So I mean, I just want to say general p-adic weights are sufficiently regular. And also, okay. Second remark is related to what it's still here. So I say, so we also want to say the Galois action is sort of mm, sort of non-generic acting on this cohomology classes below middle degree. So also we can prove something like that. So that's the precise statement. We still haven't fully worked out. So let me instead just give you an example of what we can say. So we just do the case on modular curve. Oh, I forgot to say, so just like when we look at GQP, so we look at the weights. So for the Galois action, we also want to look at the weights, and the one notion here is the Hodge sand weights. So what do I mean? So G is just GL2. Then this is just usual modular curve. Okay, and and what is not sufficient regular, or because it's type A, so sufficient regular is just regular. So the only non-regular weight with respect to SL2 is just let me just take the trivial character. It's the infinitesimal character of the trivial representation. So I can't apply the theorem in this case because it's not sufficiently regular. And indeed, H2.0 lambda 0 is non-zero. Simply because we know this is non-zero because it just sees, at least it contains, sees the connected components, so it's non-zero. But we could say the following, and we could also see the following. So let me just, well, it's a general fact that if you look at H2.1, and if you take the lambda 0 SOTP part, so I would just restrict myself to the decomposition group at P. Okay, so one useful fact is that actually this is a Galois representation of Hodge, which is Hodge state of weights 0 and 1. Okay, actually you can show both 0 and 1 will appear. So this is, some very general results. When you fix some infinitesimal character, actually you get a list of Hodge-shaped weights that will appear. In the trivial character case, it just gives you 0 and 1. But when you look at restrict to H, so below middle degree, there's only H0. And you can, because we know that on this H0, the GL2 action factors through the determinant, and by class field theory, you actually know that actually this action is smooth, in the sense that locally, for each vector, there's it's fixed by open subgroup. So in particular, the Hodge state weight is 0. So I just want to say, so you see that if we compare these, you see one is missing here. And actually, this is some very general phenomenon that below middle degree, there will always be a Hodge-shaped sand weight in general, not showing up below middle degree. So, sorry, this might be a little bit technical, but it more or less says that so just below middle degree, the Galois representation has to be smaller than what you expected, because you won't see all the Hodge-shaped weights. That's related to this non-generic. I want to say there. Any other questions? Any questions?
This one, you're in the center of the right?
Yes.
Is there a version with the whole Cartan algebra instead?
Cartan,
Like, there's one CP, with CP, this whole Cartan algebra acts in computed cohomology. So instead of looking at the center of the
you mean this levy center of the? Yeah, yes. Actually, this is more or less follow from that. So yeah, you have a more refined version of it, but it's more complicated to state.
and also can you predict not just the vanishing of whole middle degree, but maybe a bound for the
Yes, you can. Yeah, yeah. So actually, yes. Thank you for the question. So yeah, it's actually, if you give me some weight, I can predict a range of degree that's vanishing. So I can only give you an algorithm to work out such range, but I don't have a very easy formula for that.
Just out of curiosity, is the theorem false if in regular you asked it for simple covariates rather than all covariates?
I need to check, but at least type A, I don't think there's any problem. You should just. Let me think about this after the talk. Yeah, sorry. Let me quickly mention some corollary. This result. So, I also want to advertise in some sense that. So, for me, completed cohomology is some kind of universal p-adic interpolation. So once you can prove something for completed cohomology, then you can prove a lot of vanishing results. I mean, once you have some vanishing results here, you can also prove a lot of vanishing results from it. So, for example, even you only care about cohomology of the Shimura variety, just use your local system. Not this kind of very huge completed cohomology. The corollary, so which was obtained before by Kevin Lan and Junku Su. In this particular case, is that so. Way to formulate this properly. For simplicity, let me assume G is semi-simple. And take a dominant weight. GC, and then get the finite dimensional representation GC, and it gives me a C local system. V mu underline the Shimura variety. I just fix some level K. So then this cohomology vanishes below middle degree if mu plus rho is sufficiently regular. Okay. So as I mentioned, so in type ADE case, so it just says that mu is regular. But let me also mention that so actually this is also true in type BC case by completely automorphic method. So proved by Lee and Shimura. That's great. This is just assuming this is 0. Just assuming it's regular. Our method couldn't quite prove this in type BC case. Is at the moment. But I just want to emphasize that this is completely by automorphic, like use automorphic representation, but also like in the work of Lines too, our work is completely geometric. So it doesn't use anything about automorphic form. It's really just about the geometry of Shimura varieties. Okay. I have around 15 minutes. So maybe I can state another rather technical mark. So actually, so this is for finite dimensional local system. So actually, you can also replace this by some very huge infinite dimensional local system. As long as you can talk about the infinitesimal weights. V mu can be replaced by any locally analytic representation. So say K, the form P upper P, K lower P of KP is sufficiently regular infinitesimal character. Just using the when you vary the level at P, you get KP K lower P tosser, and so for any continuous representation of KP, you can attach some very huge local system on your Shimura variety. And I was just saying that if you this representation is locally analytic, just meaning that first it's Banach space representation, and then locally all the vectors are locally analytic, and then it has this infinitesimal character, and I assume it's sufficiently regular, then you have the same vanishing result. So that's why I say, so once you prove something for completed cohomology, you can just it just give you result for any other p-adic interpolation. The last remark I want to make, and then I want to move on to the proof. There are questions before doing that. Okay, so this is proof is geometric. So so what are the ingredients used in the proof? So first, the step is that the completed cohomology is defined by as you see, it's defined by vanishing cohomology. Vanishing cohomology. If you want to prove some vanishing results in general, it's difficult. But coherent cohomology, the vanish actually we know much more vanishing results, because then we can apply tools in algebraic geometry. So the first thing, the first ingredient in proof will be just to first translate the vanishing cohomology to some coherent cohomology. So it's to coherent. So for simplicity, let me assume first the Shimura variety. So I think from now on I will just fix some level at P. So let me assume the Shimura variety is compact, so that I don't need to deal with compactification. But in general, I need to use both the minimal and the toroidal compactification. So I will not do it here. And second, let me just do like there, just assume G is a semi-simple. Again, this is. I mean, in general, there's some issue with this center that you have to be more careful, but I mean, you don't really need to assume this to prove the main result. So I forgot to say so. So the proof is completely. I mean, it's based on chaotic geometry instead of complex geometry. So let me just fix identification between the usual complex number and the p-adic complex number. So in particular, my Shimura variety, well, after this identification, I got a algebra variety over CP, then I can moreover view it as a regionality space. Not in this way, HK or CP. Okay, so as I mentioned, so when you vary the level, let me also just fix KP. So when I vary the level at P, so I get a KP tosser. So in particular, any representation of KP will give me a local system. So I can just consider C lower P, which are just all the continuous functions. Continuous functions on KP. So in particular, the translation action of KP. So so you can view this as a representation of KP, depends on which side of action translation you use. Then it just gives me from it I can define a local system. Still know by CKP underline. This is a huge local system, infinite dimensional local system. Oh, I forgot to say the pro-état local system. It's a small variety. The first result we need, essentially due to Schulze, is that well, maybe it's better to separate these. So one useful fact, which was known already by Emerton, is that you can really identify completely cohomology with the cohomology of this very huge local system. So the theorem Schulze really he proved the primitive comparison theorem, and it follows from that. When you take the completed tensor product with CP, then there's a natural isomorphism between the we talk homology, this huge local system tensor with the completed structure sheaf. This is the structure sheaf on the pro-état side. So it already appearing in one stock. But the point is that so it really becomes some coherent cohomology on the pro-état side. And so here you don't lose too much. I mean, after tensing with CP, so if you can prove some vanishing result here, then it will imply the vanishing result for completed cohomology. That's first step. Step two is that we need some vanishing result in a coherent cohomology. And at least for me, the most powerful such a vanishing result, at least over complex numbers, is this Codera vanishing theorem. And so, but it was known for a long time that Codera vanishing fails. I mean, there's just counterexample in characteristic P. But I think very recently, Barga Butt, he proved almost Codera vanishing result in mixed characteristic. And the insight, at least for me, is that I think we were not using the correct structure sheaf in the past, and so the correct one is really defined by this whatever prismatic cohomology. I mean, you can define some kind of structure sheaf using this kind of perfectoidization, and it's actually not a sheaf anymore in general. But if we use that, then the Codera vanishing still holds. I mean, it actually also holds in the mixed characteristic case. So step 2 be this it will follows from results in upcoming work of Barga Butts. They are vanishing. So I would just state a corollary of his result. It's will be useful for us. So let's back showcase. Is that so here? Well, in all such Codera vanishing, we need an ample line bundle. So let me just take an ample line bundle. Shimura variety. And then it just says that below middle degree, if you consider this huge local system and tensor with L inverse, strictly speaking, so I mean, writing this way, so pi denotes the map of sets, morphism of sets from Pro-Eta side to the analytic set. Okay, so I can put back this line bundle to get a line bundle on the Pro-Eta side. And then if I tensor with the dual, the inverse of this line bundle, then the cohomology vanishes below middle degree. So we see that actually it's not too far away from what we need. So we want to prove some vanishing of this one below middle degree. Okay, so what Barga Butt's result gave us is that well, if you twist by L inverse, twist by a ample line bundle, then you have the vanishing. Now the question is how to untwist this L inverse. We just we already have some kind of some sheaf. Our inverse is 0, then we want to deduce. This is also true without twisting this out. But so actually, that's where we need this sufficient irregular condition. So I don't have much time. So step 3. So how to do this? And how to untwist this ample line bundle? Actually, this is some kind of argument already appeared in Bernstein's work on localization. So using translation functor. I will just explain a toy example and actually my favorite example. If I have time, I will just say how to apply this in our case. Probably I don't have time. So at least I want to explain this example just in the simplest case. It's the sum P1, so over complex number. So I think you all know that on P1, so we have this sequence. Vector bundles, and actually it's a non-split vector bundles on P1. And to see this, actually, if you just take the global sections, it's two-dimensional, so you get such a map. And there's how the kernel is also give you a line bundle. On P1, we have the action of SL2. So actually, this is exact sequence is also SL2 equivalent if you interpret this 2 in the correct way. So as I say, the correct way is the global section of this line bundle. So the correct one, so it's the standard representation. The representation. Then this is SL2 equivalent. And also you can just twist by any case, or for example, I can just by this K. Very bad at the numerology here, so make sure I'm correct. I guess I'm already out of time, so can I use 2 more minutes? Just like K. And the claim is that well, so if you look at the action of the Casimir operator in the center of the universal enveloping algebra of SL2, its action on OP1 K-1 is given by 1/2 of K squared minus 1/2. And the section here is half K plus Q squared minus 1/2. So this is quadratic in K. So we know that if K is not equal to the center is -1. So then these 2 eigenvalues are different. So you just get a splitting using the action of Casimir operator. So we see that if K not equal to -1, then we just see that the middle term isomorphic to the dark sum. The rest 2 terms. So in particular, if I know vanishing of the cohomology of this term, it automatically implies the vanishing of the cohomology of these 2 terms. So in this K-1 or K+1, I guess K+1 is what I want. It's just the twisting of OK by an ample line bundle, and this is exactly what I want there. And this is really splitting as sheaves of abelian groups. So as I say, so as a vector bundles, it's not split. But if you just you forget about the.
Did you say that when K0 it didn't split?
No, that's quite coherent shifts, just as shifts.
Yes. So I just forget about the whole linear structure. So let me just say, so in our case, how to generalize this argument. So so P1 will be some black variety. If you know how to define Shimura variety, you know there's some partial flag variety appearing there. It's actually the opposite one. B is actually equal to some G mod P. And this Casimir operator I already write here. So you look at the infinitesimal action. So you just think what I denote by Z there. And this K. So remember, so because we have this K, we can read the eigenvalue of Casimir. So K is very important, and in general, it will be replaced by some action of the ZM. So M will be be a levy of this parabolic, and this action actually is not clear a priori that you have such an action, but this was discovered first by myself in the case of modular curve, and in general by Juan using if you do geometric sense theory on Shimura variety. And the finally, so this K not equal to -1, we will just correspond to our sufficiently regular condition. Okay, I think I'm out of time, so let me just stop here. Thank you for your
So this bot result doesn't require you to pass to any sort of locally analytic vectors.
No.
I see. Yeah. Is there any chance that would say something about like something sort of about the Banach space, or?
Yeah, I mean, I would hope so. At least you need to put some generic condition, and I mean, it won't. I mean, it will be low